So now we look into the last part of this lecture, where we look into the last of the elements remaining to be defined from what we're seeing from the geometry of linear programs, and that is the notion of extreme point and vertex and how they connect, and also a new notion, which is the notion of basic feasible solution, which is something that we're gonna that is gonna be central when we develop the simplex method. So as we saw last week, due to the geometry of the linear programs, whenever we look into the optimal solutions, they always gonna live on one of the vertices or one of the extreme points of the polyhedral set. Unless you have that very peculiar situation that your vector is actually perfectly perpendicular to one of the facets, so then it means that any point at the facet will be optimal, which actually means that you have more than one vertex that can be optimal. If you are in R2, you can have two, and so on and so forth. But before we move on, let's try to give an algebraic definition to these elements of vertex and extreme point and so on. So let's start with the notion of vertex. So consider P as a polyhedral set, and let's look at consider this vector x that belongs to P, and let's assume that it is a vertex. If it is so, then it means that you can find a vector C to be the normal of a hyperplane, such that when you look at all points y also belong to P, they always have this relationship that means they are within one of the half spaces of the hyperplane defined with normal vector C. So this is basically illustrating the following picture that will have something better showing up in a minute. But so it basically means that if you're wondering whether X is a vertex of your polyhedral set, it will be true if you can find this, say, hyperplane here with normal vector C, that it is such when you look at all the other points, say Y, all these other points y, they have a strictly greater than relationship with that hyperplane, meaning in other words, meaning that they are strictly on one of the sides defined by the half space. So it could be, in this case, it would be that, I don't know, your polyhedron could be something like so. Your polyhedron set could be something like so. So every point y would be such that by definition you can once you found this hyperplane C with normal vector C, every other point, all the other points within your polyhedral set is such that they are going to be strictly inside one of the sides of the half space, one of the half spaces formed by this hyperplane. You see, that won't be the case if X were to be, say, here. Let's call this X prime. Then it wouldn't be the case, because you can't really find a hyperplane that contains all the polyhedral set. You could find a hyperplane that is sitting on this facet, but that's not entirely true. You have several y's that you could put that satisfy this relationship inequality. So it's basically that a vertex will be that point that for which you can find a hyperplane that meaning that the whole polyhedral set is exclusively one of the sides of the half space formed by that hyperplane. And the other important definition is the definition of extreme points. So extreme points, they are slightly different in a sense. So you say that XP is an extreme point if and you can't find two vectors also within P for which you can write X as a convex combination of them. It's very similar, really, but it's technically different. So basically, suppose you have a point X there, and this belongs to P, right? If X is an extreme point, basically what is going to happen is you can't find 2 points X and Y, or Y and Z. So let's call this Y here. You can't find a Z point within P being this polyhedral set there, such that you can write X is a convex combination of them. It won't be the case in any other case. Suppose now that we have the same polyhedral set here, and we're wondering whether this is the extreme point. You can see that you can pick, if this is X, you can pick Y here, and Z here, and definitely write X as a convex combination of both. So that at the top, it's definitely not an extreme point. So here is a picture illustrating the two concepts a bit better. So in this left-hand side here, we're talking about vertices. So for example, for this point X, you definitely can find a hyperplane for which the whole set is exclusively on one side of the half space. But then when you look at this W, you can't. You know, the only half space containing W that segregates P to the other side has a collection of points there, here specifically, that satisfy this is not strictly on one side of the hyperplane because it's exactly on the hyperplane. And this is showing the definition of extreme point. So in this case, it's saying that I cannot find 2 points on the same hyperplane, which means on the belonging to P, such that X can be written as a convex combination. But in this case, I easily can. And you can kind of, looking at these two pictures, you can see that we are almost saying the same thing differently. And there is a reason for that. As we're going to see later on, there is a result that is central for what we're doing, which basically show the relationship between extreme points, vertices, and basic feasible solutions, which we haven't defined yet, and that they are actually equivalent. So a point that is a basic vertex is also an extreme point, and it's also a basic feasible solution. So, but we'll get there. So, but you can see that it's kind of almost intuitive that they are the same thing, right? Okay. But of course, to under a computational sort of setting, we need to look into algebraic representation of these things. And that's why we'll move on and think about the notion of basic feasible solutions. So let us just define it then, a polyhedral set from law n, and let it be formed by a collection of inequalities and equalities, so in any direction. So I have greater and equal inequalities, lesser or equal than inequalities, and also equalities. And I'm just creating these sets n1, 2, and 3 to keep the indices of each. Because that's how we're not going to have P being represented by a geometrical figure for us. That's how we're going to create a P. P is going to be defined for us by a collection of equalities and inequalities. So with that in mind, we can look into the definition of active constraints or binding constraints. But we talked about that, remember, when we looked last week in the lecture. We said the active constraints were the constraints where the optimal point was living in the intersection of. And that's just a sort of a general way of saying the same thing. So suppose we have this vector x bar, it's a point x, that satisfies some of the constraints in equality for some of the indices in M1, M2, and M3. Those elements from M1 and M2, M3, for each that is the case, we say that these constraints, they are active. So satisfying the constraints in the equality. It's trivial for equality constraints, of course, but for inequality constraints, it might not necessarily be the case. So here is a picture illustrating this. Our polyhedral set is the collection, it's just given by a single hyperplane, so I only have one equality constraint, and it's given by x1, x2, x3 equals 1. So it's basically this hyperplane there, but constrained to be within the positive orthant. So technically, I actually have 4 constraints: x1 greater than 0, greater than or equal to 0, x2 and x3, so on and so forth, and this equality constraint, which gives me this feasible region right there. So we can see that, for example, picking a random point like A, at A I have 3 constraints that are active. And what are these constraints? The constraint that says that x x1 plus x2 plus x3 equals 1 because it's part of this polyhedral set P, right? So it's on this hyperplane even. And the other constraints that are active is the constraint saying that x1 is 0 and x2 is 0. So this point has x1 equals 0, x2 equals 0, and x1 plus x2 plus x3 equals 1. So these are the three constraints that are active here. I also have 3 active constraints for this point, 3 active constraints for this point, and 3 active constraints for this point. x1 equals 0, x2 equals 0, x3 equals 0. But notice that E is a point where only 2 constraints are active. The constraint associated with the hyperplane, x1 plus x2 plus x3 equals 0, and the constraint associated with x2 equals 0. So for this one, we only have x2 equals 0 and x1 plus x2 plus x3 equals 1. So only 2 constraints are active in there. See, so that's kind of representing. So you see that these are represented it's kind of something special about them, and the thing that is special about them is that they in R3 they have 3 active constraints. All right. So this is sort of the main aspect. This theorem 12 is showing the main important properties associated with when we look into active constraints in linear programs. So let us define x bar like so, and let's call capital I the set of constraints, the constraint indexes that are active at x bar. So I give you a point x bar, you look what the constraints are active, which of the constraints are active, and then you return me those constraints that are active is what I say that they live, the index of these constraints is what live in this capital I set. Once you give me a collection of active constraints, here is a collection of properties that are meant to be, they are equivalent, meaning that if one holds, then the other one holds and the other one holds as well. So if you can show that one holds, then automatically the other one holds because they are equivalent. It's almost like they're saying the same thing. One of them is there exists any vectors within AI that are linearly independent. So once you look at what constraints are active, there are going to be anywhere in Rn. So n of these constraints, when I look at the normal vector to the hyperplane forming the boundary, these vectors are going to be linearly independent, which is kind of a condition that is necessary to form a point in R2, for example, or a point in R3. You need 3 constraints to match. The span of these constraint normal vectors will span Rn. We saw what was a span 2 videos ago. In other words, for every x in Rn, you can find a linear combination of AI to express them. And that's just the definition of span. It's the space. All these linear combinations of AIs is the subspace spanned by the normal vectors AI. And the intriguing one is that the system of equation forming from these active constraints, they have a unique solution. That one is going to be really important for us because we can use this just by, if I look at my constraint and randomly select n to be active, I can immediately find what is the point that they intersect by solving this system of linear equations that will have a unique solution. So that's a really important property that we're going to use all the time when we are in a setting where we cannot really see what we're doing. We know that we are, say, at a given point that is in the intersection of n constraints, and if I pick any n set of constraints, I can solve a system of linear equations, and that takes me to a point, and that a point is the unique solution of this system. This is important for what we're doing. It's because that whenever you think of there is there are always n active constraints that are linearly independent at x bar. And that is what makes X what we call a basic solution. It's called basic solution because the active constraints at X bar, if you look at their vector, the normal vectors, they span the space. So it means that because you have n active constraints, you have n linearly independent vectors, and therefore they span Rn. So whatever point such that the active constraints, whatever point you are, that the active constraints are such that the normal vectors span Rn, it means that you are at what is called a basic solution. We'll have a picture of that to illustrate this a bit better. But let's first do a proper definition of what it means to be a basic feasible solution. Well, as you might suspect, a basic feasible solution is a basic solution that is feasible. And that's exactly what is in this definition right here. So consider the polyhedral, the convex polyhedral set P, all right? And it's defined by the linear inequalities and equalities with those sets M1, M2, M3, for example. And let this x bar be a reference point, okay? So x bar is going to be a basic solution if all the equality constraints are active, so they are satisfied, and out of the constraints that are active, n of them are linearly independent. So the active constraints include the equalities and everything else, but in a way that n of them are linearly independent. Because again, I want to look at these active constraints and think about their normal vectors, and I want to see that those vectors spanning Rn. What it means that why I'm interested in thinking that the active constraints have normal vectors spanning Rn? Well, because it is telling me an important thing. It's a vertex. We'll see in a minute. I'll have a picture. Let's not jump the gun. And also number 2 here is basically saying that now you have a basic solution. Okay, a solution, again, a basic solution is that point that when you look at the active constraints that are there, I have at least n, which with the normal vectors being linearly independent. And it is such that this basic solution, when you look at all the other constraints, they satisfy them all, including the non-active constraints or the inactive constraints, then that basic solution becomes a basic feasible solution. And that's exactly what we call the BFSs. And we're going to be talking about BFSs all the time from now on, right? So it's good to get familiarized with that acronym there. BFS, Basic Feasible Solution. Okay, so here is a picture kind of illustrating what we're talking about. So we have these 1, 2, 3, 4 constraints holding here. Okay, and this is my polyhedral set P right there. So you can see that because this is R2, a basic solution would require 2 linearly independent constraints meeting each other. Why am saying I want 2 linearly independent constraints? It's because then it means that when they cross these 2 constraints, when they meet, they form a point. They form a vertex, a point. You see? And these are, when we know from the geometry of LPs, these are going to be the interesting points that we're going to be interested in. That's why we're interested in basic solutions, because they take us straight to these extreme points, these vertices, right? So yeah, so there is a difference. It's not like all basic solutions are relevant. Or you only interested in those that actually are feasible. There's no point looking into a potential vertex. This potential vertex is not feasible, right? So for example, in this case, this point here, even though it's a basic solution, because I have two linearly independent constraints meeting there, it's not feasible because it's violating this constraint. Because this constraint is probably saying I want things on that direction, because that's how I form my vector, my polyhedral set P. So this is not satisfying this constraint for sure. Just like F is not satisfying this constraint. So they are basic solutions, but they are not basic feasible solutions. So the basic feasible solutions in this picture are C, B, C, D, and E. These are the good stuff, the potential candidates for optimal, supposing that this is a feasible region for our LP. You see? Good. And I think that the last thing that, is suspended in the air is this main result that kind of wraps up what we had to say today. And it's a result that you're going to look into the exercise sessions, which is basically this idea of connecting vertices of my polyhedral set P, extreme points, and basic feasible solutions. Given that vertices and extreme points, even though they are defined differently, once you look at a geometrical representation of them, it becomes sort of obvious that they are the same thing. It is not obvious at all that basic feasible solutions are equivalent. They are extreme points and they are vertices. And why is this result important? Well, because basic feasible solutions, they have a very geometrical way of being, a very algebraical way of being represented. So I just have to make sure I have n constraints that are active and all constraints are being satisfied. And that gives me basic feasible solutions. Done. And if I can show that they are extreme points of vertices, then it means that my solution method can just go over from basic feasible solution to basic feasible solution algebraic without having to have a geometrical representation of my problem and look for optimal solutions. And that's exactly what Theorem 14, the importance of this Theorem 14. So if you have this convex polyhedral set and x bar belonging to P. So the following are equivalent statements. If you say that x bar is a vertex, then x bar is an extreme point and is also a basic feasible solution, and vice versa. So this is the main result of this week that we're going to look into in the exercise session. And it's basically the result upon which the method to solve linear programs is based on. So some important remarks associated with how you prove this and consequences of Theorem 14. Well, the first of all is that if x is a vertex, x is by definition a unique minimizer. And to see x by definition, because remember that we said that it is a vertex if this holds for all y in P. So in basically saying that, so if your objective function is such that is, has this vector c are the coefficients of your objective function, and x is that such a vertex, then it means that whatever other point you can find in the polyhedral set is going to have an objective function that is worse than that. So this is kind of like an intuition that we're going to use next week when we prove, when we devise the notion of optimality for linear programs. But it comes from definition, basically. How we defined vertex. You'll see that the definition of extreme point is going to be more useful in other contexts, but this definition of vertex, proving that a vertex is an optimal point for LPs kind of comes from the definition of a vertex, really. And because of these equivalency, now that we know that x is also going to be a basic feasible solution, this is going to be the unique solution. This optimal solution is going to be the unique solution of a set of equations formed by the NLI active constraint. The trick is, how do I find the correct set of n active constraints? And that's going to be the trick. From all my constraints, find those n that are going to be active, that when not active, they provided me that vertex X, which is the optimal point. That's the search. That's the challenge we're going to be looking into. And perhaps one thing to be concerned that we're actually going to talk more in detail when we look into the simplex method in a couple weeks, I think, is that the number of constraints is obviously finite, right? It's the number of rows of a matrix, which is finite by definition. But it means that if we're looking at n elements within an m possible set, then you can see that things can get quite complicated quite fast, because this is a really large number. This grows really, really fast. Remember, this is m factorial times divided by n factorial, m minus n factorial, and regardless of what, this is a big number, very quickly a big number. So, and that means that especially as we go in higher dimensions, and we have more and more constraints, this starts to become problematic. By the way, remember that in this case, these constraints are including the non-negativity as well. Okay, so because last time I told you, well, we have n and n plus m constraints. So this m is playing the role of n plus m, because whenever you add a variable, you are adding a constraint. So it's more complicated than it looks initially, because this thing is also growing as we increase variables, because you have the constraint saying that it's greater than or equal than 0. So that's a challenge that we're gonna have to look into. Luckily, it turns out that it's not as big as a challenge as it could be, but it's still, in the worst case, it could mean that we have an insanely large number of candidate basic feasible solutions to look into. All right. So this wraps up the theoretical setting we wanted to develop to kickstart putting a bit looking into the mechanics of the methods that are used to optimize linear programs. What comes next from this next week is that we're gonna start at looking into the foundation of how we develop a method that, without actually seeing the geometry of our problem, how do we start from a basic feasible solution, move along adjacent to next basic feasible solutions until we find that basic feasible solution that returns us this point, this vertex that is optimal for my problem. And of course, optimality is also dependent on the objective function, right? So we'll look into this setting and how we go about moving within that region. But thanks for watching, and looking forward to see you in the exercise session. Bye.